Hello everyone, my name is Aryan. I am 12 years old. I was born in Bihar but I am living in Ludhiana for my education purpose, and for today our topic would be about the four fundamental laws. So, introduction to conservation laws and quantum physics. So, conservation laws are fundamental principles that describe the invariance of certain physical properties. The birth of quantum physics revolutionized our understanding of atomic and subatomic processes. This presentation explores the four fundamental conservation laws and their role in the development of quantum theories. What are conservation laws? Conservation laws state that specific quantities remain constant in isolated systems over time. They are essential for understanding the behavior of physical systems across different scales. These laws underpin much of classical and modern physics, including quantum mechanics. So, let me give you an example. What are these conservation laws? So, when we throw something, and if it goes in say it goes in the right direction, so we will feel and recoil to the left one to conserve the momentum. So the first law of is the conservation of energy. So energy cannot be created or destroyed, only transformed from one to another form. This principle was established through experiments and theoretical work in the 19th century. So it is fundamental to all physical processes from mechanics to thermodynamics. So, historical development of conservation of energy. So, the concept evolved from the works of scientists like Joel, Helmut Holtz, and others. It unified various energy forms, mechanical, thermal, chemical, under a single principle. So, this law then became a cornerstone for later developments in physics, including quantum mechanics. So in quantum mechanics, there is one thing that if it does not violate any laws of conservation, it will happen. So let's get to the second law, which is the conservation of momentum. So momentum is the product of mass and velocity, and it remains constant in isolated systems. So this law is vital in understanding collisions and interactions in classical physics. It laid groundwork for later insights into particle interactions at the quantum level. So let me give you an example on the atomic scale. So whenever an electron does spontaneous emission, and what is a spontaneous emission, you may ask, is that when an electron in an atom absorbs an photon and it jumps to a higher state, and so what happens to the photon's momentum, you may ask, is that when it gets absorbed, let's say it gets absorbed, and then the electron will feel a slight nudge to the opposite direction to conserve momentum. So this also happens, and this also happens when the spontaneous emission is finished. So historical context of momentum conservation. So this principle was formalized in Newtonian mechanics and confirmed through experiments. It applies both linearly and angularly, governing the motions of objects and particles. So quantum physics extended the concepts of momentum to subatomic particles, revealing new phenomena. So the third law is the conservation of charge. Electric charge is conserved. The total charge in an isolated system always remains constant. This law is fundamental to understanding electromagnetic interactions. It was crucial in developing early atomic models and later quantum electrodynamics. So, a conservation of charge. So it states that everything uh, that every charge should be conserved, and we can see in the example given, if there is a neutral body and there is a charged body nearby, what will happen that they will uh, the neutral body will absorb, and due to this the both bodies will have an average which would be to conserve charge. So discoveries that led to charge conservation. So this law was supported by experiments in electrostatics and electromagnetism. It helped explain atomic stability and the behavior of charged particles. Quantum physics refined our understanding of a charge at the particle level, including quantization. So the fourth law is the conservation of lepton and baryon numbers. So these conservation laws assert that the total numbers of leptons and baryons remains constant in reactions. They are important in particle physics, especially in understanding nuclear and particle interactions. So these laws contributed to the development of the standard model of particle physics. So this fourth law also was responsible for something bigger. It was the discovery of the neutrinos. People found that one specific reaction did not obey this law. So after finding out, they found out that there is an extra particle called a neutrino. So significance of lepton and baryon conservations. So this explains why certain particles reactions are forbidden or rare. Their violation in some processes hint at phenomena like neutrino oscillations. So these conservation principles are integral to modern quantum field theories. So let's now go to Einstein's problem. So right now we have discussed all of about the conservation of laws. So now let's see, are they applicable everywhere and what is breaking them? So the Einstein's problem. So Einstein's problem revolved around how to demonstrate that total energy was conserved within his new theory of gravity, known as the general theory of relativity. With Einstein's new equations, they couldn't find where this energy was accounted for. So David Hilbert, a mathematician, attempted to find these energy conservation equations in Einstein's theory, but only found the Bianchi identities. These identities showed energy conservation only in a completely empty universe, making them seem useless for a universe like ours, which is filled with matter. So we have discussed about the Einstein's problem, and there are few more things that I would like to say. So Einstein, let's talk about Einstein's happiest thought, which was imagining a window cleaner falling off a building. He realized that the while falling, the man would feel weightless, and anything he dropped would remain stationary to him. So this would be as he was floating outer space. This led to Einstein understanding that there must be an equivalence between accelerated motion and the action of gravity. So this was significant because he could now understand accelerating frames. So he would not have only a more general theory but also new theory of gravity. So that is the general in general relativity. So this principle of equivalence states that if you're stuck in a rocket in outer space accelerating at 9.8 meters squared, it would feel exactly the same as you were standing on the surface of Earth. So yes, let's now begin. Emmy Noether. So Emmy Noether later realized that Einstein's proposed energy conservation equation contained a pseudo tensor, meaning it does not remain the same quantity in different frames. This implied that the gravitational energy observed in one frame could completely disappear in another, which Noether believed was a fundamental mistake that disregarded the foundational principle of general relativity. And what was this foundational principle of general relativity? It was from a special relativity that anywhere in the space or the universe, the laws of gravity should remain same. And uh, Einstein had proposed that he also thought that the conservation laws held a key for understanding and giving an equation to show how the energy was conserved. So then he gave out an equation, but it contained a pseudo tensor. So and Noether also realized that it would not remain the same quantity in different frames. So for to understand this pseudo tensor, we have to understand what a tensor really is. So starting out with a scalar or a vector. If there is if there is a triangle and there are coordinates, we can give the triangle a sum of 2, and if the coordinate system is changed, it will remain the same. And this is also the case for a tensor, but a tensor, it means that it does not remain the same quantity in different frames. So if we change the coordinate system, the value and the whole thing will change. So that was not correct, and Noether realized that. And it was, first of all, it was David Hilbert who proposed that Noether, which was her assistant, should help her with this. And she was also a master in symmetry, and this is how she solved this crisis. Symmetry. So in symmetry in physics is any action that you can take that leaves an object unchanged. So for example, triangle symmetry. An equilateral triangle has three axes of symmetry where reflections leave the triangle unchanged. It also has rotational symmetries, meaning it looks the same after rotations of 120, 240 or 360. So So there was one more thing there, and symmetry. If we go for mathematical functions, so shifting a mathematical function up or down by a constant amount does not change its derivative. So this is referred to as continuous translation symmetry because it cannot be shifted by any amount. Okay, and the derivative. Uh, so it does not change the derivative, and the derivative will remain same if we change it by a certain if a by a constant. So this shift can be any amount, not just a specific fixed values like the rotations of a triangle. So the derivative of the function remains unchanged regardless of the constant added. So how symmetry gives rise to conservation laws. In an empty universe, there's nothing special about any particular point. The laws of physics are the same everywhere, meaning the universe is completely symmetric under translation in space. This spatial translation symmetry leads to the conservation of momentum, implying that an object thrown in this universe would continue indefinitely at the same speed. So let's look at Einstein's problems once again. So if I wanted to give an example in real life or in the universe, if let's imagine that if we are in space and we throw a rock, it would slow down, and common sense says that it should go on forever, but that is not, which is violating the laws of conservation. So Einstein proposed energy conservation equations, which contained a pseudo tensor, which means that it does not remain the same quantity in different frames. This implied that the gravitational energy observed in one frame could completely disappear in another, which Noether believed was a fundamental mistake. and it disregarded the principles of general relativity. So let's get to one more thing, which is translation symmetry mentioned. So it is a type of symmetry where an object remains unchanged after being shifted or moved from one position to another. In an empty static universe, there is nothing special about any particular point. The laws of physics remain the same everywhere. So this the spatial translation symmetry directly leads to the conservation of momentum, implying that an object thrown in this universe would continue indefinitely at the same speed. So, so if we also spin an object, if we let's say if I am spinning an iron rod, what would happen that let's say it rotated by 60 degrees. So what we can do is we can just rotate the whole universe by 60 degrees because it's an empty and static universe. So then it would remain to its original position, which would be conservation, which conserved itself. And this time translation symmetry is like when we throw an object in this universe, let's say it traveled a distance in, let's say it traveled 100 meters in 10 seconds. So after 10 seconds, what we can say is that we can move the 100 meters, we can move the whole universe 100 meters so that the ball will remain at its original position, which means that this universe contains uh, this translation symmetry. And then if we say this, that's true, so it means that it will just go on, which means that it has conservation of energy in it. And this applies for ourselves only. So like by considering, so this was like time translation symmetry. So that is the laws of physics are the same at slightly different times. So now Noether was able to manipulate the Lagrangian with the action framework. So after some mathematical steps, she showed that the Lagrangian will remain same and unchanged after a time, a shift, and then that it also has a specific quantity, which turns out that it's representing the total energy. So it would be like the steps plus the Lagrangian is equals to 0, which means it is conserving energy. So now it is also meaning that it has a time derivative equal to 0. This means that the total energy of the system had to be a constant in essence. So which directly gave birth to conservation of energy. And there is one more thing, the principle of least action. So by using this, Noether was allowed to mathematically derive that time translation symmetry is equivalent to the conservation of energy, thus revealing the fundamental origin of this conservation law. So the first term in the equation, like it says how much energy changes within a specific section of the universe. So let's talk about it later after some time. And there was one more thing that I mentioned was general covariance. So this was more like fundamental because it is a core tenet of general relativity. It is the idea that the laws of gravity must have the same form in every frame of reference, no matter how are we moving. So then Einstein needed to use tensors to satisfy this principle because tensors remain the same quantity regardless the coordinate system used to describe them. So this property ensures that the laws of physics look the same everywhere, even when transforming points of space-time. So Einstein's original initial proposed energy conservation equation for general relativity failed because it disregarded the foundation principle of general relativity. that was general covariance. So Einstein proposed that if the energy of the matter and the energy of the gravitational field were added, that their total would remain constant. So and that is then that was the original initial proposal of that if he would add the energy of the matter and the energy of the fields uh, were added, which would remain a constant, but it did not, because it contained a pseudo tensor which would like in one frame would be there and in the other it may completely disappear. So this meant that when we tried transformed it from another frame of reference to another, it would not remain the same quantity. So consequently, the gravitational energy observed in one flame can be disappeared in the others. So let let me give you an like another introduction to these tensors once again, because the vectors are has simpler examples to introduce tensors. A vector can be written with components that change if you use different coordinative systems. However, the underlying physical properties, the vector itself, remains the same because it has its components adjust in a very complementary way. Tensors extend this idea, having potentially more components, often arranged like a matrix. So, so it is the same thing but more advanced and it has more components in it. So, okay, so let's now move on to the next slide, the problem. So, Einstein initially proposed energy conservation equation for general relativity failed because it disregarded the foundational principles of general relativity, general covariance. Einstein proposed that if the energy of matter and the energy of the fields were added together, their total would remain constant. Noether discovered that Einstein's equation contained a pseudo tensor. This meant that when we tried to transform it from one frame of reference to another, it would not remain the same quantity. Consequently, the gravitational energy observed in one frame could completely disappear in another. So, it was a very huge problem, because if it was not dealt with, that would mean that the conservation of laws are breaking. And general covariance, as we discussed, is a very core tenet of the general relativity. It is the idea that laws of gravity must have the same form in every frame of reference, no matter how are you moving. So, Noether also put some thought on the general covariance and said that this is also an symmetry. So, like this, we will discuss it after some times. So, okay. Where will we? So, our universe does not have the perfect time translation symmetry over large time scales. So, astronomers have observed that the universe is not only expanding, but its expansion was also speeding up. So, the expansion means that the universe is not the same now as it was billions of years ago, and it will be different billions of years ago from now. Therefore, over large time scales, the universe is not symmetric in time. Since time translation is linked to the conservation of energy, the absence of this symmetry on large scales means that energy, as we usually think of it, is not conserved in our universe. So, this is pretty shocking, and I also discovered it, and it was pretty hard to believe that energy is not conserved in the whole universe. So let's give an example. A photon traveling through the expanding universe loses energy. So when that photon was released about, like, let's say 380,000 years ago, it has lost 99.9% of its energy and became a microwave. And that is how we see the microwave background radiations. So, so the continuity equation. So we'll talk about this and about the terms in this equation. So it describes the flow of a conserved quantity, ensuring that nothing is created or destroyed within a system. So let's take an example of a pipe and water that is flowing into it in sections. So the first term in this equation represents how the amount of water changes within a specific section of the pipe, and the second term represents the difference between the water flowing in and the water flowing out of the system. When these two terms cancel to zero, it means that the total amount of water in that section only changes. So water flows in or out, not because it is being created or destroyed within the section. So it is like when we minus first term, the minus when we minus the first term from the second one, we'll get 0, because the total amount of water in this section only changes as water flows in or out, because it is not being created nor being destroyed. And in the context of general relativity, Emin author found a similar continuity equation for energy. So in this context of general relativity, a local symmetry refers to the ideas of physics looking the same in any small region of space-time, regardless of how are you moving or your specific frame of reference. It implies that in a small area you can change your frame of reference or transform the point of space-time around as much as like. The physical laws remain consistent. So that was about the local symmetries. So if you want to do that continuity equation for the whole universe, what we can do is that we can have the pipe has space-time and the water has energy. So the first equation term in the equation represents how much the amount of water, but now it would be with energy changes with a specific section of the space-time, and the second term represents the differences between the energy flowing in and out of that specific section of space-time. When these two terms cancel to zero, it means that the total amount of energy in this section only changes. Water energy flows in or out, not because it is being created or destroyed within the section. But what is happening? That there are cracks in the universal pipe. It means that so it is also about the curvature of the space-time, and to get an specific equation for that unit or for the section of space-time, what we have to do is we have to get the first term and the second term, and we also have to add the curvatures of the space-time to get the conservation of energy law for that specific space-time. So why do we see that conservation of energy is still applicable in our life? But there is one more thing: general relativity. In the context to it, she found a similar continuity equation for energy. So in the context of general relativity, a local symmetry refers to the ideas that the laws of physics look the same in any small region of space-time, regardless of how are you moving or a specific frame of reference. It implies that in any small region, you can change your frame of reference or transform the points of view around as much as we like. So where does that extra energy go? It does not go anywhere. It just simply decays. It simply disappears. And for us on the earth, these laws are still applicable because of some things called the local symmetries, and it is all due to this general covariance, and That is all because of this general covariance, which states that the laws of physics are this for gravity are same for everywhere on the universe. So that creates a local symmetry. In the context, it is called a local symmetry, and the laws of physics in that small region of space-time, regardless of how are moving or anything else, the physical laws of the four fundamental laws will remain consistent. So, it so if we look back at David Hilbert, the mathematician, which attempted to find the energy conservation equations in Einstein's theory, but only found the Bianchi identities, which showed that energy conservation only happens in an useless or empty static universe, and it is useless for ours. So, so he was right all along, but he did not put extra thought in the Bianchi identities, or we would have gotten it very further, very presently. So, moving on to the next slide. So, time translation symmetry, let's talk about it more. So, by considering a time translation symmetry, that the law of physics are the same at slightly different times, Noether was able to manipulate the Lagrangian with the action framework through a series of mathematical steps. She showed that if the Lagrangian remains unchanged under a time shift, then a specific quantity, which turns out to be representing the total energy, which has a time derivative equal to zero. This means that the total energy had to be a constant in essence. So this principle of least action allowed Noether to mathematically derive that time translation is equivalent to the conservation of energy, thus revealing the fundamental origin of this conservation law. So, so as we said, like in an empty static universe, if a ball is moving and it moves 10 meters in 10 seconds, we can do is what that we can move the whole universe to make the ball go at its original place, and that is called time translation symmetry, which also gives rises to the origin of the conservation of energy. And what we can do is rotational symmetry. We can also do with it with rotational symmetry. So when we move, like say a steel rod by 60 degrees, and we can what we can do in that empty static universe is that we can rotate the whole universe by 60 degrees, so that the metal pipe will remain at its same place. So that will also give rise to conservation laws. So, but our universe does not have the perfect time translation symmetry. Over large time scales, we have observed that the universe is not only expanding, but its expansion is getting more and more. So this means that the universe is not same as it now was billions of years ago, and it would be different from years ago now. So this therefore over large time scales, the universe is not symmetric in time. So therefore over large time scales, the universe is not symmetric. And if we have to make the universe symmetric, what we can what is to be done is that the expansion of the universe should be like static or constant. So then we can do then the symmetry can be there. So the continuity equation which Noether found out, uh, So in this, what she had to do is that she had to imagine the universe as a whole pipe, and then pipe, and that pipe is made up of space time, and the water in it is the energy. So the first term in the equation represented how much amount of water changes within a specific uh, section of the pipe, and the second term represents the difference between the water flowing in and the water flowing out of the system. When these two cancel to zero, it means that the total amount of energy in that section only changes. Energy flows in nor out, not because it is being created or being destroyed within the section. So, but in this universe spectrum, what happens is that there's a curvature in it, and that curvature we have also to add the curvatures, the energies of the space-time curvature, and then we have to add it. Then we will get the energy conservation laws for that specific time space. And gender covariance also gives rise to the local symmetries, which are there. And that is why we in real life we see these physical laws are remaining constant. So our universe does not have the perfect time translation symmetry over very large time scales. Astronomers have observed that the universe is not only expanding, but its expansion is also speeding up. This expansion means that the universe is not same now as it was billions of years ago, and it will be different billions of years from now. Therefore, over large time scales, the universe is not same as now. So therefore, over very large time scales, the universe is not symmetric in time. Since time translation symmetry is linked to the conservation of energy, the absence of this symmetry on large scales means that the energy, as we usually think of, is not conserved in a universe. For example, a photon traveling through the expanding universe loses energy. So, so yes, uh, so yes, everyone. This was our presentation. In this presentation, we talked about symmetries, how they gave rise to the conservation of laws. We discussed about Einstein's problem, where he was trying to get an conservation equation for his theories. There was David Hilbert, who found mistakes in it about the Bianchi identities. There was Emmy Noether, who gave us many things, and she was a master at symmetries. She noticed that Einstein's initial proposal had pseudo tensor in it, and which was not in real tensor. And by considering time translation, she got to know that the energy in an that energy must be conserved in a empty static universe. But our universe is not empty, and it is not static, it is dynamic, and it grows every time. So she also had to include the curvatures of the space time for an conservation law for that specific amount or that specific place in space time. So yes, thanks for everyone for joining us and seeing this presentation. Thank you.